All right, we're out of the studio today and we're in our innovation center where we house our 3D printers. This allows us to have quick and easy access to rapid prototyping and iterative design based off user feedback. Capabilities we have here are really, really nice because we're able to quickly and accurately prototype our designs. One of the really cool things about LineMaster, we have some excellent people who know what they're doing. And I'm gonna pull in 2 engineers who know the ins and outs of the prototyping and production process.
So my name is Sean Lewis. I'm the Director of Engineering here at LineMaster. My background is primarily mechanical, so I'm deeply involved in a lot of the designs work that we've done here. Talking about 3D printing today and some of the different ways that we use it in our development process, from ergonomic studies to proof of concept, to fitment, to temporary tooling, just to go through some of the benefits that we have realized utilizing that equipment.
My name is Christian Smutnik. I'm an applications engineer here at LineMaster. I work with customers primarily in terms of coming up with something that's functional, has all the functional requirements required of their console, as well as being a cost-effective solution. So something that meets their needs without excess cost or complexity, to give something that has the least amount of lead time as well.
Yeah, so for early product designs, one of the things that we're just looking at is the overall switch the right shape? Does it fit? Does it have the right range of motion? Does it align with the way that the operator is going to be standing while they're using it? Just getting an overall feel for it and understanding how the ergonomics are going to react when this thing is actually built. There's definitely phases down the road where we're using it for more refined things like fit up. This would be an example of something that we're using for test fitting. So one of the things that is hard to simulate in a CAD environment are things like wire routing. We see that as always shows up on our risk analysis documents. Hey, if you're putting this thing together and you've got 6 wires in an enclosed space, what is the likelihood that one of those wires gets pinched when you put the main parts together? So we're trying to optimize that, and this is an example of, we haven't even spun the board yet, or we've spun an early version of the board and it's being built, and we just want to print a replicant of how the form of that board is going to look. So we can see where the wires connect to the header, where they come in the housing, simulate how those parts are going to come together, make sure there's enough of a lead here or a service loop as applicable, and how those two things are going to basically fold together when it comes into finished assembly, and see where are the pinch points, which anybody that's tried to route wires in CAD knows how fun that is. It can be misleading and time consuming. So we always like to do that in a real environment, but that's just one of many examples of how a 3D printed part can bridge that gap, even from a CAD environment to something that you can look and feel with your hands.
And to Sean's point, one of the other things that we could evaluate is we'll try different springs when we're evaluating this. So especially with something with a 4-spring design such as this, where it can be actuated from any side, figuring out what those forces are and how it interacts with the user is also something that we can evaluate at this stage with multiple different spring rates, heights and such, to evaluate different things like preload and such.
Yeah, and then some of the other things, even just to talk about a further refinement, which, now that 3D printing has gotten as accurate as it has, we can simulate some of the things like an interference fit. So one of the things that we like to do for ease of manufacturing on our product is we put a slight interference fit at the bottom of a spring pocket so that as the operator is putting the switch together, they're retained in the housing. And some of those are, you can simulate it in CAD and show, maybe there's a 5 or 10 thou interference fit, but you don't necessarily know how that's going to snap and feel right on a workbench. So we like to put just enough of a slip fit there where they might be able to invert it for an operation where the two halves are coming together. But so with some of the nuance points that we're able to capture before committing to tooling, which everybody knows once you've tooled something, the cost and timeline for tweaks goes up drastically. So we like to get all those kinks worked out in a 3D printed environment as far as we can before we get into cutting steel. So another way that we use 3D printing during our design phases are a lot of our switches have a variable output. And to create a variable output, we are using a sensor, in this case, a Hall sensor, to generate that signal. So simulating the range of motion of the magnet in relation to its position to the Hall sensor on the circuit board, 3D printing allows us to show exactly where that magnet is going to be, exactly where its relation is into the Hall sensor. We can simulate a lot of those things mathematically, but this lets us do it in real world. So we always like to get an exact, or as close to an exact replication of that in the design phases, so we can start looking at, things that could cause failure, nuances in the stroke, because maybe it's not a direct head on to the sensor. You're going to have some rotation in that mix as well. And just having a real part in hand to test those things out is critical for us.
And we can also play with different strengths of magnets too. So we can, just like springs, we can trade them out and test different magnets and different thicknesses, diameters, to make sure we're also centered over the Hall sensors to make sure that we are most accurate in that reading.
So having 3D printing to show customers a design concept is really invaluable, because us being foot switch specialists, we know how something is going to feel underfoot based on its size, based on similar designs. But somebody that's new to it, they're really going to want to test drive the thing. You want to put it on the floor, you want to step on it. It's funny, one of the things that we experience all the time as foot switch manufacturers is you hand somebody a prototype, they set it on a table, they want to actuate it by hand and see how the ergonomics feel. And we always caution people that that's not really the way that you want to evaluate the thing. Really, you want to put this on the floor and put it under your foot and see how it feels. And those things vary quite a bit if you're either going to be performing an operation seated or if you're going to be standing. Because if you're seated, you're going to be operating the foot using dorsiflexion, and it's going to be fatiguing if we have a high spring rate or a high resistance force in the spring system there. Or if you're standing and you're just shifting body weight, maybe you want to go a little bit higher. So there's always those nuances there that you really want to interact with the device before we move this thing along into a production phase. So we try to get a lot of that work done on the front end and just let the user experience how this thing is going to operate once it's in production.
And that allows them to have an early look too in terms of the switch and how it operates, and also the force that Sean was talking about. So if we send them a quick 3D printed prototype just to get it under their foot, and they say, hey, we need this to be a little bit more force, we can quickly swap out springs and get that part rolling. Also, if those changes that are suggested require tooling changes, if we had already tooled up for it instead of just 3D printing, that can cause a lot of excess cost and delays and such within the prototyping of the design. So just printing something quickly allows for a toolless first look at the device as a whole, and then the prototype conversation can go from there in terms of development and different features and such from there.
And a lot of what you're seeing on these prototypes too, so the treadle gets a lot of the attention focus to it, but one of the things that a lot of these devices carry are auxiliary inputs. So a button or some other input device somewhere on the switch housing. So one of the things that is not apparent or not obvious when you're designing something is, your foot is more clumsy than your hand in a lot of cases, and you want to have enough separation between that auxiliary input and your main input, or auxiliary input to auxiliary input. So that lets us simulate, that it's possible that as you're hitting this device, you may overlap your shoe or your foot over onto the button and press the two devices at the same time. It lets us do things like provide a little bit more separation between those devices, maybe put some kind of divider between those two devices. So it's always good to actually take this thing for a test drive, get it in front of a user group. There's a wide range of variety in the size of people's feet, the footwear they're using. While we confirm that it works at the extreme, we try to make it nominal for the average user. So there's always a little bit of give and take there, but having a physical part to simulate those environments is key. So we've been 3D printing here at Linemaster for a long time, probably over 10 years now at this point. And we started adopting printers when the first few consumer grade printers were out in the market, going all the way back to when MakerBot was making printers, and we were seeing that first wave of them hit the market. We adopted it for proof of concept to see that it would work, and then over the years we've upgraded to more and more commercial machines, starting with FDM and now adopting some of the newer SLA equipment that we have, and Chris can speak to some of that a little bit more.
After the MakerBot, we went to a Markforged, which is still FDM, but it allows for some very robust materials to be used, as well as some infill materials, and just the repeatability of the printing process itself and the surface finish. So then after that, we just got SLA machines from Ford Labs. So that allows us to do three things. That allows us to go to a larger format in terms of we can print parts that we wouldn't be able to print on the FDM. It also allows for better surface finish and a little bit higher accuracy. So the layer height is lower, so we get more accuracy in terms of that. The biggest thing is the speed. So something that would take us over 24 hours With FDM on the SLA machines will take us 3-4 hours, something like that, if that long. So that's the biggest thing. And then if you're going to print multiple parts at once, there's no time penalty for that. So you can fill up the build plate and you can get parts much faster in higher volumes as well.
As we've talked about, we use 3D printing for a lot of different use cases here, but there's three main categories that we use it for. So the first one that is pretty common is just prototyping what a concept may look like, getting a first draft of what the part's going to be replicated in production. Another use case that we've found with the 3D printing, with the newer equipment that we have, because of the resolution of the parts and just because of the accuracy, we're able to do some short run mold tooling. So these are a couple of examples on the table. This is actually a tool that was developed to make a gasket. So one of the things that we have not been able to 3D print great, but we've found a great bridge in, is temporary tooling elastomeric parts. So this is a part that will be made out of silicone in production, or it may actually end up being a TPU, but this is something that we can make a tool for, get a couple of shots. We're actually injecting right into the 3D printed cavities, and then we're able to simulate a very close to production part. So matching things like the durometer of a rubber to check a gasket seal, or just how that rubber is going to flex when the product is in use. You want to talk a little bit about this one, Christian?
Sure. So another thing that we've been able to prototype, just to get the feel of how it looks and the functionality and make sure fitment, is receiver. So this is a receiver dongle, and we were able to replicate this process, just doing a quick 3D printed mold and then putting the parts inside of the mold and then injecting it. In this case, this was basically like a simple version of like a hot glue gun to inject it with, just to get an idea of what this would look like and some of the issues and difficulties we might have with this process.
Yeah. And that's in production going to be a low pressure molding operation. So, but it lets us work through some PFMEA and set up some of the pressures, how the internal parts are going to react. And then the obvious one is, how does that part interact in your hand? Does it give you a good purchasing surface to insert and remove that from the console that this gets plugged into? So you can see we start pretty crude. This is not a very refined part, but it lets us, what we like to say here, fail fast and find out what's going to go wrong with this thing when we build it, and iterate through a couple of different processes really quickly. We can do this one and say, hey, something in here didn't work or didn't quite feel right. The material didn't flow through the way that we thought. And by, if we do that in the morning, we can send another round of parts to the printer and have it before the end of the day. So to Christian's point on some of the SLA equipment, it's incredibly fast how fast you can throw a CAD file over and get a part in your hand. So very, very supportive on the iterations.
And another pro of the SLA machine too is the surface finish at which it prints for things to be used like molds. So historically we might have had to, if it was a FDM part, we might have had to sand or do something different in order to use it as a mold. But with the SLA machines, we can use it as is and just mold directly into it without any surface finish concerns.
Just talking about surface finish again, going back to some of the prototypes that we've got as we get a little bit closer to production. So you can kind of see some of these are rough, maybe even some print errors on some of them. But as we refine the programs and get closer to production, we can do things like tumble or sand out some of the surfaces, even Cerakote those parts or spray those parts and paint them. So if that part is going to be a casting with paint on it in production, you'd be hard pressed to tell the difference between how that thing is going to look in a prototype phase versus a production phase. So what we have on the table today is actually more rough concepts. We got some of the early work. This is actually a product that we demonstrated this year or this past year at Medica. So there's some more refined versions of that was produced for our marketing group, and then some physical samples to show our customers. But we wanted to show some of the earlier stages in our conversations today, because these go through many stages of the design in a lot of these. So we may have 4, 5, 6 rounds of parts before we get to the final version of it, and it doesn't make sense to finish all of them to the final version. So if we're just checking fit, we leave them rough and we keep it moving. So this here, what we have on the table, is another just example of some of the ways that we've implemented 3D printing. So just on a trip down to the floor, we had observed one of the operators kind of struggling with some of the drivers that we were using. We have a ton of these little micro drivers for either set screws or maybe turning potentiometers on a product, whatever the case may be. But small diameter device like this is a little bit fatiguing in the hand. So we said, hey, do you want something on there to give you a little bit better of a grip? And the original concept was, hey, just put a wheel on here that makes the outer diameter of that tool a little bit larger so you can spin it with your fingers. But they used that for a little bit, and then some other operators got involved and said, I like that, but maybe a little bit smaller for my hand, or they wanted a little bit different texture or geometry on there, and that went around, and then kind of voted on it, or voted between a couple different users, and said, I like the diameter of the one, but I do like the height of that one. So you can kind of see the iterations here of that. Now we've got a full diameter of the first one, but the height of the second one. And a little bit different on the texture here, try to give them a better grip. We put some ridges in here. Originally thinking that might be enough to stop the wheel from rolling, but with a little bit of energy, you can still get it to come across your table. So that led us to version 4 here, where we made it octagonal, so it definitely is not going to roll. But we actually found that the octagonal geometry on this made it fit in your hand and kind of index it around as you did perform rotations with the tool. But you can kind of see that fit in here and worked well. So we got positive feedback on this one. I think we were probably at like the 90% approval rating, maybe 95% approval rating. But one of the things that we discovered is there's actually 2 or 3 different sizes that we use. We want to make sure it fit all 3. So we moved that mounting surface in so that it would engage the tool a little bit deeper onto the grip shaft. And we kind of improved the texturing on a little bit, and then the kind of icing on the cake was we threw our logo on there just so we could show that off. Found a convenient or a nice clean workaround to get our operators on board with that.
So one of the other things that we had gotten feedback from the shop floor on is just ease of assembly of this system. So we have a channel, the treadle, and the base plate and toe loop assembly. So we came up with this SLA 3D printed work aid, which basically allows for the channel to be set in to the work aid, and then we set the treadle assembly into the work aid as well, and tuck the routing in there. And then we can set the base plate and toe loop assembly on top of that. And then we can then insert the fasteners, and it becomes a very repeatable process, decreases the amount of time required to assemble all of these things, and just makes the operators' lives that much easier. So we got some feedback initially too that this was actually more rigid than we were expecting, so it floated and didn't align as well as we thought it would. So we got some more feedback from the floor, and our next version of this fixture is actually going to help to align this better in terms of a clamping fixture so that it will be more repeatable. They won't have to hold things as they're assembling it. And so this made it easier, and now the next version is going to make it even easier for them on top of that. So at LineMaster, we're always looking to evaluate new technology, which will allow us to benefit you in the long run, to allow you to go to market faster and with a better product with more features.
All right, that was really informative. I hope that helped kind of guide you through how we use 3D printing here at LineMaster, both in the prototyping phase and actually in our production facility itself, making tools and jigs that help us produce the best product possible. Again, my name is Hayden from LineMaster. Don't forget, stay switched.